Hello and welcome. Tonight, instead of asking the enormous questions of the cosmos, how it began, where it's going, or what lies beyond, we're going to turn inward to the soil beneath our feet. There, a different kind of question waits for us. Simple to ask but difficult to sit with. What if we're not the first? Not the first minds to wonder, not the first hands to build, not the first species to chart, explore, and imagine. What if, before pyramids and satellites, before cave paintings and bedtime science channels, another civilization, one of Earth's own, rose, thrived, and then vanished without leaving obvious traces behind? I'm not talking about mythical continents swallowed by the sea or alien visitors dropping in to lend a hand. I mean something more grounded, stranger, and perhaps harder to prove. The idea that long before humans, another intelligent species might have developed a civilization here. Not one imported from the stars, but one homegrown, biological, born of this same planet. It could have thought, built, and created in ways we can barely recognize. And yet, it could have disappeared so completely that Earth itself erased the memory, folding it back into stone, water, and silence. If that sounds like the premise of a science fiction story, you're not wrong. It has the shape of a novel or a late-night tale. But it's also a scientific question, one that quietly circles through conferences and geology labs. It's been whispered in papers and mused about at the edges of cosmology. The question is not whether we'll stumble upon skyscrapers buried in Antarctica or smartphones hidden inside coal seams. The real puzzle is subtler. If an advanced civilization had existed millions of years ago, would we even know? Could traces of it have survived the relentless grind of time? Earth is a recycler, a restless sculptor. Its surface isn't fixed. It churns, folds, erodes, and rebuilds. Mountains rise and collapse. Oceans open and close. Continents drift, split, and collide. What was once land becomes seafloor, and seafloor one day pushes back into mountains. Wood decays, metals rust, plastics crumble, bones dissolve. Fossils are rare not because life was rare, but because fossilization requires an almost miraculous alignment of conditions. Rapid burial, mineral replacement, protection from erosion. Even then, luck must carry that fossil across millions of years without it being destroyed, so the real challenge isn't imagining a civilization. It's imagining how fragile its traces would be across vast stretches of time. Leave a modern city alone for a few hundred years and plants creep over concrete, water undermines foundations, and steel corrodes. In 1,000 years, the skyline is gone. In 1,000,000, what remains has been folded into stone. Our proud towers and glowing screens are temporary against the patient hands of geology. And yet, here we sit in this brief overlapping moment, you and I, connected by sound and thought across miles and seconds, asking whether this world once carried another story before us. Where are you listening from tonight? What time is it for you? As you let these words slow your thoughts toward rest. It's strange, isn't it? To talk about ancient civilizations lost in unimaginable time, while sharing a present that feels so small, so fragile. Wherever you are, whenever you are, I'm glad you're here. If you find yourself drawn to questions that stretch beyond easy answers, if the slow unraveling of deep mysteries helps you drift into sleep, then you're in the right place. Feel free to support this quiet journey by liking or subscribing. Though there's no pressure, think of it as leaving faint footprints on a trail we may someday follow together. Now, let's settle in. Lie back if you can. Let your breath match the unhurried rhythm of the earth itself. Imagine time not in hours or years, but in tectonic drift, in the rising and crumbling of mountains, in oceans forming and fading. We are about to step backward, not through human history, but through the deep silence of geological time. Before we can ask if others came before us, we must first understand the immensity of time itself and how ruthlessly this planet wipes its own slate clean. When we say ancient history, we usually mean the pharaohs of Egypt, the builders of Stonehenge, the scribes pressing the first symbols into clay. At most, that's 10 or 12,000 years ago, a span that feels distant to us, but in Earth's clock, it's closer to the present than to nearly anything else. Whole libraries already spill over with mystery and speculation about those early days, and yet they are still only a blink, a soft flicker, against the backdrop of deep time. Because the Earth is not just old, it is staggering in its age. About 4.5 billion years, give or take, stretching back into an almost unimaginable depth. For most of that time, there were no humans, no mammals, no land-dwelling creatures at all. Life spent billions of years in the ocean, first as chemistry, then as microbes, then as slow experiments in form. Most of Earth's story is written not in monuments or artifacts, but in stone layers and forgotten seabeds. And those layers don't preserve evenly. The Earth doesn't keep a diary. It erases as much as it writes. Wood rots, stone wears, metal dissolves. Even bones, those hardest of reminders, crumble back into dust more often than they fossilize. The record is spotty, filled with gaps longer than all of recorded human history. To survive millions of years is already remarkable. To be discovered afterward is rarer still. So, as a thought experiment, imagine 100 million years ago, in the middle of the age of dinosaurs, something else evolved. Something upright or not. Maybe it walked the land. Maybe it lived in the sea. Maybe it never built with stone or metal at all, but with something else, something fragile, something we would not even recognize as technology. Imagine it developed society, culture, intelligence, then vanished. Catastrophe, climate, or the slow fade of time erased it. What would remain? Would we ever know it existed? This is the sobering part. We are not permanent either. For all our satellites and skyscrapers, our archives and museums, our own record is just as fragile. The question is not only whether others came before us, but whether anyone after us will ever know we were here. When we think of deep time, the kind of time that stretches far beyond the limits of human imagination, we often picture it as a straight line. A ruler laid across eternity, with little ticks marking when dinosaurs walked, when continents split, when the first forests grew. But the truth is less neat. Earth's history isn't a timeline you can measure with a school ruler. It's a shifting palimpsest, a book written and erased over and over again, sometimes leaving only faint impressions on the page. Imagine you're standing in a canyon. The walls rise above you, painted with bands of stone in shades of red, brown, and gold. Each band is a layer of time, pressed down, compacted, and revealed only because water carved its way through. To us, it looks like art, like nature's mural. But to a geologist, it's a record. That thin strip of white might represent thousands of years when a shallow sea covered the land. That darker band might record a swamp, or a volcanic eruption, or the slow accumulation of sand blown in from distant deserts. Together, these walls are not decoration, they are memory. And yet, they are incomplete memories. For every canyon that preserves a chapter of Earth's story, there are countless others erased completely. Wind and rain level mountains. Oceans swallow coastlines. Rivers cut valleys and then fill them again. Entire continents slide beneath one another, their surface layers melted back into the mantle. If civilizations had come and gone 100 million years ago, most of what they built would have ended up erased in just this way. Think about the oldest human artifacts we've found, stone tools chipped by hand. They date back a few million years at most, and that already feels impossibly old compared to the pyramids or the Great Wall of China. But they're still recent, geologically speaking. What would a billion-year-old artifact look like if it existed? Could it survive at all? Maybe not. Maybe the very best preserved relics would have long ago been compressed into stone, their original shapes unrecognizable. A skyscraper could become sandstone. A bronze statue might corrode into dust, its trace indistinguishable from natural minerals. Even if something were to survive, would we recognize it for what it was? This is where the Silurian hypothesis comes in. It sounds like science fiction, but it's a genuine thought experiment raised by scientists. If another industrial civilization had risen on Earth before humans, how could we detect it? The answer isn't to look for cities or monuments. They'd be gone. Instead, we'd have to search for chemical fingerprints, subtle shifts in the geological record that don't have obvious natural causes. For example, consider plastics. Right now, plastic is everywhere. Floating in oceans, buried in landfills, drifting as microfibers in the air. If humanity disappeared tomorrow, most of those plastics would break down in a few thousand or million years, far too short to be noticed in the long run. But some might survive, pressed into sediments, leaving odd chemical signatures that a future species could puzzle over. They wouldn't find bottles or bags. They'd find strange carbon traces, tiny clues that something once manufactured synthetic materials here. Or think about agriculture. By reshaping land, farming leaves patterns visible from space, fields, irrigation systems, artificial channels. Over millions of years, those patterns would vanish, but the sudden appearance of vast monocultures, plants of uniform types spread across the planet, might leave pollen signatures in the geological record. Future geologists could wonder why, at a certain moment in time, diversity collapsed and a handful of species became dominant. Even our fossil fuels, the burning of which marks our current age, would leave behind a chemical scar. The sudden spike in carbon dioxide, the isotopic shifts in the atmosphere, the traces of combustion byproducts. All of these would show up as a strange anomaly in Earth's rocks. It would whisper to anyone looking closely, something unusual happened here, something with intelligence and industry. Now extend that thought backward. If there had been another civilization, say 100 million years ago, what traces would remain? We wouldn't find their tools. We wouldn't uncover their stories. But maybe, just maybe, we'd find anomalies. Pockets of unusual metals in the crust. Odd isotopic signatures hinting at combustion or synthetic chemistry. Patterns in the fossil record where biodiversity collapsed suddenly, not because of an asteroid impact, but because of something else, something more deliberate. The unsettling truth is that, even if such signs existed, they would be almost impossible to distinguish from natural processes. Earth has experienced mass extinctions many times, 5 great ones that we know of, plus countless smaller die-offs. Volcanoes can alter climate dramatically. Asteroid impacts can wipe out entire ecosystems. Shifts in ocean circulation, changes in oxygen levels, the rise of new species. All of these can leave signatures that mimic what we might expect from an ancient industrial civilization. So even if another intelligence once flourished here, its traces might be buried under explanations that feel perfectly natural. This is what makes the question so haunting. It's not about whether we'll someday dig up a fossilized smartphone or a hidden city. It's about whether, in the grand sweep of deep time, civilizations might come and go like sparks, bright, brief, and then gone, their light absorbed into the dark fabric of geology. And it forces us to confront something humbling, that our own presence here, our own skyscrapers and satellites, may be just another spark, brilliant for a moment, then folded back into stone and silence. Take a moment with that thought. Notice your breath as it comes and goes. Notice how small a single life feels in the immensity of deep time. And yet, also notice how extraordinary it is that we are here at all, able to ask these questions. The Earth doesn't often produce minds that wonder. The fact that yours is wondering now is rare, fragile, and deeply meaningful. Wherever you are listening from, your bedroom, your living room, maybe even through headphones as you drift into sleep, let yourself feel the strangeness of being part of the story. You are not outside of it. You are inside the same Earth that carried trilobites, dinosaurs, forests, and glaciers. You are part of the same experiment that may or may not have produced others long ago. Whether we are first, last, or somewhere in between, our time here is precious. If you're finding your eyes heavy, that's okay. These questions aren't meant to be solved tonight. They're meant to open gently like doors and then let you step through into rest. Tomorrow will still be waiting with its alarms and tasks. But tonight, you can drift in the long silence of Earth's history, carried not by answers, but by the comfort of wonder. When we talk about extinction, the mind usually jumps to dinosaurs. A giant rock falls from the sky, the planet shudders, and a dynasty of creatures vanishes in what feels like a single heartbeat. But mass extinctions are not rare interruptions in Earth's story. They are its rhythm. Again and again, life has flowered, spread, and then been cut down. The fossil record reads like a music sheet with long pauses, notes missing, whole sections torn out. What if one of those pauses wasn't entirely natural? It's an uncomfortable question because science prefers clean causes. Asteroids, volcanoes, climate shifts. These are testable, measurable. They leave behind signatures we can track. But a civilization, one that used tools, energy, and resources in ways we might not easily recognize, that's harder. The traces might be so faint that we could mistake them for randomness, or else so woven into natural processes that we wouldn't even know where to start. Let's imagine a scenario. It is 150 million years ago, in the middle of the Jurassic. Dinosaurs roam the land, but somewhere else. Perhaps in coastal shallows, perhaps deep within forests. Something stirs. Not human, not mammal, but intelligent in its own way. Maybe it doesn't stand upright. Maybe it doesn't speak. Maybe it doesn't carve monuments. But it learns to manipulate its environment, to organize, to alter landscapes on purpose. Suppose the species, whatever shape it took, lived for a few million years. In that span, it might have harnessed fire, altered ecosystems, maybe even developed its own version of industry. Not smokestacks and cars, but something subtler, techniques that left chemical or ecological scars. Then a catastrophe or slow decline ended them. The dinosaurs continued, none the wiser, until their own sudden end, and the intelligent species slipped into silence. Could we detect such a ghost? Geologists would look for anomalies. Layers of rock enriched with unusual metals. Isotopic ratios that don't fit the expected cycles. Sudden bursts of extinctions not well explained by volcanoes or asteroids. But Earth is noisy. Its history is filled with chaos. One extinction blends into another. One climate event masks another. The deeper you go into time, the blurrier the record becomes. This is the heart of the Silurian hypothesis. Not a claim that someone came before us, but a recognition that if they had, the evidence might be invisible. The planet is too efficient at recycling itself. Nothing on the surface is guaranteed to last. Not cities, not machines, not even bones. Take bones, for instance. The fossil record is built on them, yet they are rare miracles. For every trillion creatures that have lived, only a handful fossilized. And of those fossils, only a fraction have been discovered. Most are still buried, waiting, or have already eroded away. Now imagine an intelligent species whose population was tiny compared to the teeming swarms of fish, reptiles, and insects around them. Even if millions existed, their remains would still be vastly outnumbered by other life. The odds of finding one recognizable fossil from them might be near zero. Even our own record is fragile. Think of modern humans. If we vanished tomorrow, how much of us would still be visible in a million years? A billion years? Skyscrapers would crumble in centuries. Roads would vanish under forests. Plastics would break down, metals would corrode, glass would shatter. Perhaps the most durable things would be nuclear waste encased in stone, or spacecraft that escaped Earth's pull. But on the ground, silence. There are a few things that could outlast us. Deep mines and tunnels might leave scars in the rock. Vast amounts of processed minerals, metals extracted from, or could create odd chemical signals. Our industrial age might leave a thin line in the geologic record, a band filled with plastics, fly ash, and isotopic anomalies from fossil fuel burning. To a geologist millions of years from now, it would look like a strange, sudden event, a mystery blip in the rock. Now step backward in imagination. Could there be similar blips in older rocks? Anomalies we've already seen but explained away? For example, scientists have found sudden bursts of carbon release in the past, events where the planet warmed dramatically in geologically short periods. Some are explained by volcanoes or methane release. But what if, just hypothetically, one was the fingerprint of an ancient intelligence? Of course, there's no proof of that. Natural explanations are stronger, but the idea lingers. The farther back you go, the less clear the record becomes, and the easier it is for extraordinary events to be lost. This leads to a larger reflection. Permanence is an illusion. Civilizations, no matter how advanced, are temporary. They rise, they flourish, and they vanish, sometimes in centuries, sometimes in millennia. The Earth itself ensures this. Tectonics grinds everything down. Climate shifts erase landscapes. Even the sky itself changes. Stars move, constellations warp, cosmic radiation washes clean. Nothing holds still long enough to be eternal. And yet, there's a strange comfort here. If others did come before us and were erased, then we are part of a much larger pattern. We are not isolated, but echoes in a chorus too vast to fully hear. If we are the first, then our responsibility is heavy, because it means we are the pioneers, the opening note in a song no one else has sung. If we are somewhere in the middle, then we are part of a chain, inheriting the silence of the past and passing on whatever trace we can manage. Picture it for a moment. A planet with layers of forgotten civilizations, each one wiped nearly clean, each one leaving only whispers in the stone. Not cities, not books, but chemical shadows, isotopic footprints, faint patterns in extinction events. A palimpsest of minds, written and erased, over and over. It is possible, maybe even likely, that we will never know. That the truth, whether we are alone in time or part of a hidden lineage, will remain sealed beneath kilometers of rock. But the very act of wondering connects us to that lineage, real or imagined. The question itself is a kind of bridge, a way of reaching across silence. So, as you listen now, think of your place in this chain. Think of the way your heartbeat, your breath, your quiet presence is part of the same earth that has rolled and folded through billions of years. Think of how small we are, and yet how rare it is for the universe to ask about itself. That is what intelligence does. It wonders. And maybe, just maybe, long before us, something else wondered too. Let that thought be your lullaby. Let it drift through you like a tide, gentle, persistent, ancient. Tonight, you don't need to solve it. You only need to rest in it. The Earth has been here for billions of years. Can hold this question a little longer while you sleep. When we speak of ancient history, our minds typically conjure images a few thousand years old. The pharaohs of Egypt anointing their tombs, the enigmatic builders of Stonehenge aligning monoliths with the stars, the earliest known scripts etched into Sumerian clay tablets. Even when we stretch our historical imagination to its absolute limit, to the dawn of human agriculture and the first settled communities, we are only traveling back about 10,000 or 12,000 years. In geological terms, this is not even a blink. It is an infinitesimal fraction of a second in the planet's long day. That entire span of human civilization is closer in time to this very moment than it is to almost anything else that has ever happened on this earth. And yet, to us, it already feels like the deep, almost unknowable past. A period vast enough to fill libraries with mystery, debate, and endless speculation. But the Earth is old. Not just old, but staggeringly, incomprehensibly old. Not millions, but billions of years. Approximately 4.54 billion years, give or take a few hundred million. To truly grasp this scale, our human-centric time frame is utterly inadequate. Let's try an analogy. If the entire history of the Earth were compressed into a single calendar year, our species, Homo sapiens, would appear on December 31st at about 11:52 p.m. The whole of recorded history, from the Sumerians to now, would flash by in the final 14 seconds before midnight. The Industrial Revolution would have started a mere 2 seconds ago. For the overwhelming majority of that immense timeline, there were no humans. For most of it, there were no mammals, no dinosaurs, no trees, no fish. For vast stretches, there was no complex life on land at all. Life spent billions of years as single-celled organisms, swimming in primordial oceans, patiently waiting, evolving in microscopic obscurity. And yet, despite how empty that sounds, this was the period when most of Earth's story was written. It was written not in books, but in rock. Layer by agonizingly slow layer, stone upon stone, in a language that speaks slowly and forgets quickly. Our planet does not keep a diary. It is not a meticulous archivist. It does not preserve everything equally. Wood decays, metal rusts, fabrics disintegrate, and bones dissolve in acidic soil. Time does not just pass. It acts. It is an active, destructive force. It buries, it melts, it crushes, it shifts, and it erases. Mountains, which we see as symbols of permanence, rise and are ground down into sand. Oceans open up and close again, their floors swallowed back into the mantle. Entire continents drift across the globe, collide with unimaginable force, and are torn apart. Every few 100 million years, the very face of our world is redrawn. So when we look at it from this perspective, the problem is not that some evidence gets lost over time. The problem is that the survival of anything for more than a few million years is an extraordinary, almost miraculous event. The default state is erasure. This is the stage upon which our thought experiment must be set. A stage defined by a near-total planetary amnesia. To understand the monumental challenge of finding a long-lost civilization, we must first appreciate the relentless forces that would work to erase it. The Earth is not a static museum. It is a dynamic, violent, and constantly churning machine. Its primary engine is plate tectonics, the slow-motion drift of continental plates across the planet's surface. This process operates on timescales that make empires look like fleeting moments. Continents collide, forcing the land to buckle and fold into colossal mountain ranges like the Himalayas. Elsewhere, they pull apart, creating vast ocean basins. More importantly, this system is a planetary-scale recycling plant. Through a process called subduction, oceanic crust and anything on it is constantly being forced beneath the lighter continental crust, where it plunges into the searing heat of the mantle to be melted and reformed. If a civilization had built its coastal cities on a plate destined for subduction, its entire physical existence would be literally and irrevocably wiped from the surface record, melted down into magma. Any evidence would be gone, not just buried, but unmade. Then there is erosion, the patient sculptor of worlds. Wind, water, and ice are tireless agents of destruction. A mountain range that once stood miles high can be reduced to rolling hills over tens of millions of years. Rivers carve canyons through solid rock, carrying billions of tons of sediment out to sea. Glaciers act like immense bulldozers, scraping landscapes down to the bedrock. Any structure, no matter how robust, is subject to this constant, gentle abrasion. It is a war of attrition that stone and metal cannot win. What nature doesn't grind down, it buries. Sedimentation is the flip side of erosion. The sand, silt, and mud washed away from the land settles in layers on seabeds, in lakes, and across plains. Over millions of years, these layers can become thousands of feet thick, burying the world of a previous epoch under a new geological reality. What was once a surface is now deep underground, compressed by immense pressure and cooked by geothermal heat, its materials undergoing a slow transformation into new forms of rock, a process known as lithification. The very act of preservation, burial, can be a form of destruction, as it subjects any artifacts to forces that can crush, deform, and chemically alter them beyond recognition. This is the Earth's paradox. The same processes that create the geological record are the ones most responsible for destroying the information within it. The rock cycle is a cycle of forgetting. The planet's surface is a palimpsest, a manuscript that has been written on, scraped clean, and written on again over and over for billions of years. Each new epoch overwrites the last, leaving only the faintest, most distorted ghosts of what came before. Looking for the clear and unambiguous ruins of a city from 100 million years ago is like trying to read the original text on a parchment that has been reused 1,000 times. The signal is almost entirely lost in the noise of the planet's own ceaseless activity. Therefore, the absence of evidence is not, in this case, evidence of absence. It is the expected outcome of a planet that is fundamentally hostile to the preservation of history. Let's ground this geological reality in a more familiar context: our own civilization. We tend to view our creations, our skyscrapers of steel and glass, our sprawling concrete highways, our global data networks, as enduring symbols of our power. But they are profoundly fragile when measured against deep time. Let's conduct a thought experiment. Leave a modern city like New York or London to its own devices. Within a few decades, the plants would return, their roots cracking pavements and foundations. Within a few centuries, water damage, rust, and decay would bring down most buildings. After a few thousand years, the city would be an almost unrecognizable, forest-covered ruin, visible perhaps only to a trained archaeological eye as a series of strange, overgrown mounds. Now, fast forward a few million years. Subject that ruined city to the forces we've just discussed: erosion, sedimentation, and tectonic shifting. What was once a landlocked metropolis might now be at the bottom of a shallow sea, buried under layers of mud. What was once a coastal hub could be on a tectonic plate being subducted into the Earth's mantle. The steel that framed its towers would have long since oxidized into rust and dispersed. The concrete would have crumbled and its chemical components leached into the surrounding environment. Our plastics might survive a bit longer, but they too would break down into microparticles, eventually forming a thin, strange layer in the sedimentary rock, a plastiglomerate, but not a smartphone. This isn't science fiction. It is the known trajectory of materials based on geology and archaeology. We already know that finding traces of even recent prehistoric human activity, a 50,000-year-old hunting camp, for example, is incredibly rare. Not because our ancestors were inactive, but because Earth is an efficient recycler. This brings us to the fossil record, our primary window into the history of life. Many assume it is a comprehensive library, but it is, in reality, a book with most of its pages torn out. The conditions required for fossilization are incredibly specific and rare. Of all the billions of organisms that have ever lived, only a minuscule fraction have ever become fossils. Most that die simply decompose, are eaten, or dissolve. To become a fossil, an organism typically needs to be buried rapidly in sediment to protect it from scavengers and decay. Then, over eons, its organic material must be slowly replaced by stable minerals from groundwater. Finally, the rock containing that fossil must survive millions of years of geological turmoil without being crushed, melted, or eroded away. And then, by sheer luck, it must be re-exposed on the surface just in time for a paleontologist to find it. This is a lottery of cosmic odds. The fossil record is therefore deeply biased. It heavily favors marine creatures with hard shells or bones that lived in environments prone to sedimentation. It tells us almost nothing about soft-bodied creatures or life that existed in highlands where erosion, not deposition, is the dominant force. Now, apply this logic to a hypothetical intelligent species. What if they were few in number? What if they lived in a mountainous region? What if their biological makeup didn't include hard bones? The chances of any one of them becoming a fossil would be vanishingly small. To expect to find a skeleton, the smoking gun of a prior species, is to demand winning a lottery that may never have had a ticket. And this challenge isn't just for bones. Tools, buildings, and other artifacts face the same grim odds. Unless a civilization built on a monumental scale using incredibly durable materials like granite, as the ancient Egyptians did, and in a geologically stable area, the probability of us finding their handiwork millions of years later is almost zero. The silence in the geological record is not necessarily an empty silence. It could be the sound of a slate that has been wiped clean. Given these immense geological hurdles, you might wonder if anyone has ever seriously tried to formalize this line of inquiry. The answer is yes. In 2018, two scientists, Gavin Schmidt, director of the NASA Goddard Institute for Space Studies, and Adam Frank, an astrophysicist from the University of Rochester, published a paper that tackled this very idea head-on. They weren't proposing that an ancient civilization actually existed, a point they were careful to emphasize. Instead, they were asking a crucial methodological question. How would you even detect a short-lived industrial civilization in the geological record if one had existed millions of years ago? They gave their thought experiment a name, calling it the Silurian hypothesis. The name was a somewhat cheeky reference to a classic episode of the British sci-fi show Doctor Who, which featured an intelligent reptilian species, the Silurians, that had ruled the Earth in the distant past. While the name was playful, the science behind it was serious. Their paper shifted the search away from the conventional archaeological approach of looking for physical artifacts the fossilized bones or buried cities that are so unlikely to survive. Instead, they proposed a geochemical approach. They asked, what kind of planetary footprint, what kind of chemical scar would an industrial civilization like our own leave in the rock strata? Could such traces already be present in the geological data we have, misinterpreted as natural phenomena? They were proposing to think like forensic detectives who arrive at a crime scene millions of years too late. There is no body, no weapon, and no witnesses. All that's left is the scene itself, the planet. The only hope for solving the case is to look for subtle, anomalous traces left behind in the environment, a technosignature embedded in the rock itself. This reframing is the core of their hypothesis. It acknowledges the near certainty that direct evidence would be erased and focuses on the potential for indirect evidence to survive. An industrial civilization, they argued, fundamentally alters its planet's biogeochemical cycles in ways that might be detectable across geological time. The very act of burning fossil fuels, producing industrial fertilizers, creating synthetic materials, and even nuclear fission could leave a lasting fingerprint, a whisper in the stone. Their work transformed a philosophical musing into a testable scientific proposition. It provided a toolkit for what to look for. Instead of digging for a needle in a haystack, they suggested analyzing the entire haystack for an unusual chemical composition. In doing so, they raised an uncomfortable and fascinating possibility. Perhaps we have already seen evidence of a prior civilization but simply didn't know what we were looking at. Perhaps an unexplained spike in carbon dioxide or a strange sedimentary layer from the Eocene epoch wasn't a natural event, but the faint, ghostly echo of a world that once was. The hunt was no longer for a ghost, but for its shadow. What would these geological shadows or technosignatures actually look like? The Silurian hypothesis outlines a series of potential markers that our own industrial age is currently laying down in the sediment markers that could be a blueprint for finding a predecessor. The most significant is a disruption of the global carbon cycle. By burning vast quantities of fossil fuels, we are releasing ancient carbon back into the atmosphere. This changes the ratio of carbon isotopes, specifically the ratio of carbon-13 to carbon-12, in the air, oceans, and in the shells of marine organisms. This isotopic anomaly, known as the Seuss effect, will be clearly visible in the rock record for millions of years. A geologist in the far future could see a sharp, negative spike in the delta superscript 1 superscript 3c record and infer a massive, rapid injection of fossil carbon into the atmosphere, a hallmark of industrial activity. Another powerful signature comes from nitrogen. The invention of the Haber-Bosch process allowed humanity to produce industrial fertilizers on a massive scale, fundamentally altering the planet's nitrogen cycle. This has led to huge algal blooms and dead zones in the oceans, creating layers of black shale rich in organic matter and with a distinct nitrogen isotope signature. Another clear sign of technological interference with planetary systems. Then there are the entirely novel substances we have created. Plastics, for example, are now ubiquitous. While they break down, their microscopic remnants will settle into sedimentary layers, potentially creating a unique and identifiable stratum. More persistent are synthetic molecules like polychlorinated biphenyls, PCBs, or long-chain perfluorinated compounds, PFAS, which do not occur naturally and are incredibly durable. Discovering a concentrated layer of such complex, unnatural molecules in ancient rock would be an almost irrefutable sign of a past technology. A more dramatic, though hopefully unlikely, signature would be from radioactive isotopes. A global nuclear war, or even widespread use of nuclear power, would distribute long-lived artificial isotopes like plutonium, 244 or curium 247 across the planet. These elements have half-lives of tens of millions of years, making them a smoking gun technosignature that would be unmistakable to any future civilization capable of analyzing rock strata. Finally, there's the evidence of mining and mass resource extraction. The quest for rare earth elements and other metals would create unusual concentrations and patterns of these elements in sediment layers near industrial centers. Another geochemical anomaly that nature would be hard-pressed to explain. The search, then, becomes a hunt for these anomalies. Scientists are already studying past climate events, like the Paleocene-Eocene thermal maximum, PETM, 56 million years ago, a period of rapid global warming and a massive carbon isotope excursion. While currently attributed to natural causes, the Silurian hypothesis forces us to ask, could any such events be the signature of a forgotten industrial age? As of now, there is no evidence to support this, but the question itself is transformative. It serves as a mirror, reflecting our own impact on the planet. By defining what a past civilization's footprint might look like, we are simultaneously cataloging the permanent scar our own is leaving behind. Whether we find another civilization or not, this search teaches us about our own legacy. A legacy written not in monuments of stone, but as a faint chemical whisper in the deep, silent rock of Earth. What might remain of a vanished civilization is unlikely to be grand ruins or intact structures. Instead, we'd look for subtle anomalies buried in the rock record, hints that something artificial once shaped Earth's chemistry or stratigraphy. First, consider isotopic fingerprints. Every human activity, from burning fossil fuels to mining ores, alters the ratios of carbon, nitrogen, and oxygen isotopes in the environment. Over millions of years, such shifts diffuse but not completely. Geologists can detect tiny deviations in isotope ratios in ancient sediments that don't align with known volcanic or biological processes. If an earlier species had industrial-scale energy use, we might find unexplained carbon-13 or nitrogen-15 excursions in strata dating far beyond our own era. Next, synthetic molecules. Plastics and chlorofluorocarbons are molecular signatures we created in the 20th century. Plastics degrade slowly, but fragments and byproducts can become chemically bound into sedimentary rock. In principle, chemical analysis of deep-time shale could reveal anomalous organic polymers, chains of atoms arranged in ways biology never does. Such molecules would stand out against the background of kerogen and natural hydrocarbons. We could also search for technofossils, minerals or alloys whose composition suggests smelting or refining. For example, platinum group elements concentrated in patterns inconsistent with meteorite impacts or hydrothermal vents might hint at intentional extraction. A layer enriched in metal alloys, bronze, aluminum, or even exotic superalloys would be a geological puzzle if it appeared in sediments hundreds of millions of years old. Another clue lies in climate perturbations. A civilization that cleared large swaths of forest, pumped greenhouse gases into the atmosphere, or rerouted rivers would leave a mark on paleoclimate records. Ice cores, tree rings, and carbonate deposits preserve carbon and oxygen isotope trends. Unexplained rapid warming or cooling events, decoupled from volcanic eruptions or orbital cycles, could signal large-scale biogeochemical engineering. Finally, anomalous sedimentary structures might betray artificial construction. Straight, parallel cuts in rock layers, analogous to quarries or canals, would look odd against the curves of natural erosion. Seismic imaging of the crust might reveal geometric voids or chambers that resemble buried cities, but dating and interpretation would be monumental challenges, I and some. The hunt for a prehistoric civilization is a hunt for ghosts in the geology. Small chemical irregularities, unexpected isotopic excursions, strange concentrations of metals, or peculiar structural patterns. It's akin to forensic science on planetary scales, where the corpse is Earth itself and the crime scene spans eons. We end, as we began, under our feet, in the stone and soil that form the world's slowest archive. If we search and find nothing, it tells us as much about ourselves as it does about the past. It confirms the fragility of legacy and the ruthlessness of planetary processes. But even if we did uncover compelling anomalies, the burden of proof would be immense. Establishing that a chemical signature or metallic deposit results from intelligence, rather than a rare volcanic event or an unusual biological bloom, requires extraordinary evidence. And the deeper we look, the more we realize how easily time carries all secrets away. Perhaps the greatest lesson is humility. Humanity stands at a crossroads. We are young in geological terms, barely a moment on Earth's 4.5 billion-year timeline. Our epoch of industrial transformation, the Anthropocene, is measured in centuries. Yet we are already altering planetary systems on scales that future geologists will struggle to interpret. In searching for predecessors, we discover our own impermanence. So lie back, let your mind drift through ages, and imagine the Earth as a vast palimpsest. Every mountain range, every ocean basin, every fossilized leaf is a scribble in a margin note, an echo of processes both ancient and ongoing. The silence of deep time humbles our stories and magnifies our curiosity. If a civilization came before us, it left only faint footprints in the sand of epochs. And if we leave a mark at all, will it be enough for some distant future explorer to notice? Thank you for joining this journey into the abyss beneath our feet. Whether you're listening from a city apartment, a mountaintop, or a remote field, you are part of a conversation that spans eons. Keep asking questions, keep looking closely, and remember, Earth remembers, but it also forgets. As we continue our journey into the silence of deep time, we advance with determined steps in pursuit of questions that push the boundaries of science, contemplating a mystery that even the most sophisticated technologies of today seem unable to solve. Can we detect traces of a civilization that may have lived millions of years ago? The answer to this question requires more than just technology or archaeological techniques. It demands an interdisciplinary perspective, a complex research program that combines the planet's geochemical processes, evolutionary biology, geophysical methods, AI-supported data analysis, and even philosophical inquiries. First, high-resolution underground radars and seismic tomography devices can be used to detect anomalies hidden in deep sedimentary layers. Despite geological deformations over millions of years, these devices can capture clues of unusual structures such as straight lines, symmetrical voids, or familiar geometric patterns. Simultaneously, microscopic mineral examinations conducted at the laboratory scale may reveal traces of metal alloys or relatively rare element concentrations that natural processes fail to explain. Another method involves chemical analyses of core samples extracted through deep seamless drilling. This can uncover pre-plastic synthetic polymer residues, molecular isomorphisms similar to chlorofluorocarbons, or unusual hydrocarbon chains. Radiometric dating techniques clarify the temporal context of these traces, while geochronology experts compare the findings with known natural climate changes and mass extinctions to determine whether they result from natural phenomena or artificial intervention. This long-term research will function like a laboratory that tests the true capacity of time travel, attempting to reconstruct the actions of once living beings from incomplete and fractured data. Artificial intelligence will play a critical role here, offering persuasive mechanisms to extract patterns from massive datasets, distinguish signals inconsistent with ordinary geological variations, and highlight potential remnants of civilizations. For instance, if carbon isotope fluctuations cannot be explained solely by volcanic eruptions, or if rare earth elements exhibit a distribution indicative of deliberate mining activities rather than region-specific volcanic processes, such qualitative data may be interpreted as traces of pre-human conscious activity. Another dimension of this research is paleoecological analysis. If sudden and large-scale changes in forest cover are detected through pollen samples found in different layers, this could be considered indirect evidence of large-scale agriculture or deforestation activities. Layers that show signs of intense industrial activity over a period of time may narrate the story of an ancient civilization to future geologists through isotopic signatures resembling a corona ring. Beyond all these scientific efforts, we must also approach this question from philosophical and ethical perspectives, because searching for traces of another civilization means confronting humanity's own finitude and its impact on the planet. We begin by envisioning a global network of subsurface scanning platforms that operate continuously at scales from square meters to thousands of square kilometers. These platforms combine high-resolution ground-penetrating radar arrays, distributed passive seismic sensors, and low-frequency electromagnetic tomography to construct four-dimensional maps of crustal heterogeneities. By correlating seismic wave velocity anomalies, dielectric permittivity variations, and magnetic susceptibility signatures, we can identify features that deviate from expected geological background, such as voids with planar walls, mineralized fractures with unusual geometry, or stratigraphic disruptions inconsistent with natural depositional processes. Each detected anomaly is tagged in the Terran Anomaly Index, a geospatial database that records location, depth, approximate age, and signal strength metrics, facilitating cross-comparison and prioritization for further investigation. To resolve ambiguities inherent in geophysical signals, coring missions are launched from mobile drilling units capable of extracting continuous bedrock cores up to several kilometers deep. These cores undergo non-destructive analyses first, X-ray fluorescence scanning to detect elemental anomalies, hyperspectral imaging for unusual mineral phases, and neutron activation analysis to reveal trace rare earth element enrichments that do not conform to volcanic or hydrothermal genesis. When a core section exhibits multiple concordant anomalies, such as a narrow band enriched in aluminum-silicon composites with trace platinum group elements co-localized alongside synthetic polymer microfragments, the sample is quarantined for more detailed laboratory study. In controlled cleanroom environments, specialists employ ultra-high-resolution mass spectrometry to characterize isotopic ratios of carbon, nitrogen, oxygen, and selected metals, searching for deviations from natural fractionation pathways. Machine learning algorithms trained on vast libraries of both modern industrial emissions and natural geochemical processes flag candidate signatures. For example, a carbon-13 depletion profile that matches intensive combustion of fossil carbon stocks far exceeding known volcanic outgassing events, or an elevated nitrogen-1,5 ratio indicative of large-scale biomass fixation and fertilizer application. These flagged intervals prompt targeted experiments in nanoconfocal microscopy, revealing polymer morphologies and crystallographic textures that serve as technofossils, molecular structures man-made in origin, yet preserved for eons in lithified sediments. Parallel to geochemical detective work, paleobotanical and palynological teams reconstruct ancient environments by extracting microfossils, pollen, spores, diatoms from sediment matrices spanning suspected horizon layers. Advances in single-grain genomics and proteomics now allow retrieval of molecular biomarkers from microscopic inclusions, enabling researchers to identify abrupt shifts in flora diversity or the sudden disappearance of keystone species, which might indicate deforestation or monoculture practices. Geochronologists apply state-of-the-art uranium lead and argon-argon dating to volcanic ash layers bracketing anomalous intervals, pinning down temporal windows with uncertainties of less than 0.1%. Complementing these terrestrial studies, orbital platforms equipped with hyperspectral and thermal imaging sensors scan exposed cratons and desert pavements, searching for planar patterns in reflection spectra that could betray buried foundations or large-scale earthworks. Interferometric synthetic aperture radar, INSAR, data over decades reveals minute surface deformations, subsidence or uplift, consistent with the collapse or erosion of massive subsurface cavities. When integrated, these data layers build a three-dimensional forensic geospatial model of each region, which is then subjected to computational fluid dynamics simulations to assess how hypothetical artificial structures might have influenced groundwater flow, sediment transport, or microclimates. Regions showing persistent anomalies across independent modalities advance to the gold tier of the search, warranting the deployment of autonomous undersea gliders, cave-penetrating drones, or even strategic seismic blasting surveys to peer beneath ice sheets and deep marine sediments. Yet beyond the purely empirical tactics lies the equally important domain of theoretical modeling and simulation. By constructing evolutionary scenarios that explore divergent paths of intelligence, intelligent cephalopods adapted to ocean currents, avian analogs with bone-based toolkits, or even arboreal primates that left no durable structures, researchers expand the range of expected signatures. Agent-based models simulate how such species might exploit resources, modify landscapes, and produce chemical byproducts over hundreds of thousands of years. These simulations generate synthetic data sets that feed back into the anomaly detection algorithms, continually refining their sensitivity to both familiar and entirely novel forms of technogenic imprint. This iterative loop, observation, sampling, simulation, and algorithmic learning, constitutes the core of Terran Archaeology 2.0. But as we refine our capacity to hunt for geological ghosts, we must also grapple with the interpretive and ethical dimensions of our endeavor. What threshold of evidence justifies the claim of prehuman intelligence? How do we avoid false positives caused by unusual but natural phenomena, such as hydrothermal vent mineralization or biogenic methane seeps, that can mimic industrial signatures? An international consortium of geoscientists, archaeologists, philosophers, and ethicists must draft rigorous standards akin to the criteria for exobiology or dark matter detection. A minimum of 3 independent lines of corroboration, reproducibility across multiple sites, exclusion of all plausible natural explanations, and transparent peer review. These standards must be codified in an open-access archive to prevent premature sensationalism and to ensure that claims withstand the scrutiny of a diverse scientific community. Should we one day uncover compelling evidence, a polymer metal composite layer dating back 150 million years, or an abrupt isotopic excursion incompatible with known Earth system dynamics, the implications would be profound. We would be forced to reconsider the uniqueness of the human saga, to acknowledge that intelligence on Earth is not a solitary phenomenon but a recurring possibility. Our understanding of evolutionary theory, planetary habitability, and the longevity of technological civilizations would all need recalibration. Moreover, the existential impact on human self-image could be seismic. Religions, philosophies, and cultural narratives centered on human exceptionalism would face unprecedented challenges. Conversely, if the search yields nothing conclusive, that null result itself becomes a testament to the relentlessness of geological processes and the fleeting nature of intelligence. It would underscore how extraordinary it is that any trace of Homo sapiens survives beyond a few hundred millennia, let alone billions of years. In either outcome, the long-term endeavor to detect deep-time intelligence confirms our drive to explore, to question, and to place ourselves within the vast, complex tapestry of Earth's history. As research teams expand their efforts, leveraging ever more sophisticated tools and theoretical models, we edge closer to answering the question that has haunted us since we first gazed at the stars and wondered, are we alone? The difference now is that we are looking inward, into the silent strata beneath our feet, seeking echoes of possible predecessors in a world that memory erodes as relentlessly as wind and water sculpt its face. This is the final frontier of archaeology, not merely to exhume ruins, but to decode the geologic palimpsest itself for traces of ancient minds. In doing so, we embark on a journey that spans not only space but unimaginable depths of time, bridging the chasm between the momentary flicker of a civilization and the eternity of planetary transformation. The methodological frontier continues to expand. Beyond seismic tomographies and mass spectrometric forensics, quantum sensors promise sensitivity to trace element distributions at submillimeter resolution, while next-generation neutrino detectors may one day reveal asymmetric isotope patterns deep within Earth's core. Integrating these tools with global data networks demands an open science infrastructure where raw measurements, anomaly indices, and interpretive models are shared in real time. Cloud-based geospatial platforms will allow researchers from any continent to overlay tectonic histories with polymer fragment maps and palynological records, effectively democratizing the investigation. Crucially, standardized metadata protocols and rigorous provenance tracking will prevent the cherry-picking of sensational results, channeling collective intelligence toward reproducible discoveries rather than isolated claims. Parallel to hardware advances, software innovation reshapes our approach. Artificial intelligence pipelines trained on synthetic deep-time datasets, generated by agent-based simulations of hypothetical civilizations, can detect patterns that elude human analysts. Deep learning architectures, fine-tuned on both natural geochemical fluctuations and engineered signatures, will flag candidate horizons with probabilistic confidence scores. Yet transparency remains paramount. Every flagged anomaly must be accompanied by an explainable reasoning trail, detailing which features, be they isotopic peculiarities or geometric regularities, drove the model's decision. Only through this marriage of machine efficiency and human interpretive judgment can we avoid both Type 1 errors, false positives, and the more insidious Type 2 errors, overlooking true faint signals. These technical evolutions have profound philosophical ripples. If a credible pre-human civilization emerges from Earth's strata, it would shatter the notion of human exceptionalism. Our species, often portrayed as a singular intelligence that reshaped the planet, would become just one iteration in a much longer lineage of conscious actors. This reframing challenges religious doctrines, ethical systems, and cultural narratives that hinge on humanity's uniqueness. It would compel us to redefine personhood, moral responsibility, and the very concept of cultural heritage. As scholars debate whether a non-human intelligence could generate art or ethics, artists and writers will likely pioneer new mythologies, blending epistemology and imagination to weave stories about the ancestors we never knew. Ethically, the search carries its own responsibilities. Our field methodologies, drilling kilometers into bedrock, deploying autonomous vehicles across fragile ecosystems, and launching orbital surveys, must adhere to stringent environmental safeguards. Baselines for permitted disturbance should mirror those in deep-sea mining and planetary protection protocols, ensuring that in unearthing one civilization's traces, we do not inadvertently harm living communities or geological features of outstanding universal value. Furthermore, indigenous groups and local stakeholders must be partners rather than passive observers. their ancestral knowledge respected as a complementary form of place-based wisdom. This inclusive approach transforms the hunt from an extractive enterprise into a collaborative quest for Earth's forgotten narratives. On the horizon of citizen science, an engaged public can play a vital role. Smartphone apps capable of analyzing soil spectra, community-driven drone mapping initiatives, and open-access 3D models of anomaly sites empower enthusiasts to contribute real data. Platforms like GeoSleuth or TerraArchive could gamify the search, rewarding users who identify unusual sediment patterns or report legacy mine shafts that merit professional follow-up. In doing so, the boundary between expert and layperson blurs, fostering a global network of stewardship that watches over both present and past civilizations. Looking beyond Earth, parallels emerge with exoplanetary exploration. Just as astronomers scour distant worlds for biosignatures, Terran archaeologists seek technosignatures beneath our feet. The cross-pollination of methods, spectroscopy, radiometric dating, climate modeling, enriches both disciplines. Missions to Mars or Europa might one day hinge on protocols perfected in deep-time Earth studies, while orbiter observations of fluvial networks could inspire new ways to detect buried aqueducts or canals on ancient continents. By treating Earth as a proving ground for archaeological astrobiology, we refine our capacity to ask whether intelligence anywhere in the universe leaves indelible marks in stone. Culturally, the impact of this research may catalyze new forms of expression. Visual artists could excavate palimpsests of imagery, layering satellite maps with fossil-inspired sculptures. Musicians might compose sonatas that resonate with seismic frequencies recorded from deep-time cores. Writers will speculate on the fate of a vanished species, using their narrative to reflect on climate change, resource depletion, and the fragility of knowledge. Museums and digital exhibits will reconstruct shadow cities in virtual reality, inviting audiences to wander labyrinths of hypothetical ruins, spaces where tangible evidence eludes touch, yet stimulates collective wonder. Yet, for all the technological promise and cultural ferment, the core challenge remains epistemic humility. Geological processes conspire to erase, distort, and disguise. The faintest trace may be buried beneath kilometers of rock or masked by mineral metamorphosis. For every anomaly we uncover, we must interrogate alternative natural explanations, hydrothermal events, tectonic faults, microbial biocrusts, before invoking intelligence. This rigorous skepticism is not cynical but essential. It honors the silence of deep time while preserving our capacity to recognize genuine echoes. As we close this chapter, we envision a world where the study of prehistoric intelligences is both a scientific discipline and a cultural movement. One where data streams flow freely, ethical guardrails protect our planet, and philosophical reflection keeps our ambitions grounded. The question that launched this journey: could a civilization have risen and fallen before us without leaving recognizable monuments? Evolves into a broader meditation. What will our own legacy be? In the end, the greatest discovery may not be finding another intelligent species, but understanding how to leave a trace worthy of deep time. A legacy of curiosity, collaboration, and care that endures even as continents drift and erode. A consortium of international agencies, akin to the Intergovernmental Panel on Climate Change but dedicated to paleotechnosignatures, should codify guidelines for sampling, data sharing, and interpretive thresholds. These standards would ensure that future expeditions adhere to rigorous reproducibility, prioritize minimal environmental impact, and respect local communities' rights. The consortium's charter should specify conditions under which anomaly data is classified, ensuring proprietary commercial interests do not impede open scientific collaboration. Next, the technological frontier. As quantum gravimeters reach parts per trillion sensitivity, they will detect subsurface density anomalies attributable to ancient voids or constructed foundations. Neutrino tomography networks, originally conceived for nuclear non-proliferation monitoring, could be repurposed to image mantle heterogeneities aligned with deep-time excavation shafts. Meanwhile, advances in synthetic biology might allow the reconstruction of extinct microbial lineages from ancient enzyme fragments, revealing biological footprints of metallurgical or chemical processes once employed by precursor intelligences. The imperative is clear: fund modular research platforms that integrate these diverse instruments into interoperable fleets of landers, drones, and submersible vehicles, all communicating via mesh networks designed for low-latency data fusion. Equally vital is the cultural and ethical dimension. Recognizing that any discovery of pre-human intelligence carries profound implications for human identity, the discipline must embrace decolonized research practices. Indigenous epistemologies, steeped in narratives of ancestral guardianship and land-embedded knowledge, offer complementary frameworks for interpreting sedimentary anomalies. Joint stewardship agreements should grant traditional custodians co-ownership of subsurface data, ensuring that findings become part of living heritage rather than extractive curiosities. Environmental justice principles must govern fieldwork. Drilling permissions, deep-sea coring, and seismic surveys should only proceed with full environmental impact assessments and benefit-sharing agreements for affected regions. In parallel, education and public engagement must evolve. Curricula from primary schools to universities should incorporate modules on deep-time archaeology, inviting students to consider the fragility of legacy and the agency of Earth itself. Virtual reality simulations of hypothetical shadow cities, rendered from integrated anomaly indices, can provide immersive learning experiences without disturbing actual sites. Citizen science platforms, enhanced by smartphone-based spectroscopy attachments and low-cost magnetometers, empower global volunteers to contribute measurements that feed into the Terran Anomaly database. Liability protections and training certifications will ensure quality control while democratizing the hunt for geological ghosts. On the policy front, international governance is imperative. A United Nations resolution on deep-time heritage could formalize protection zones where drilling or excavation is heavily regulated. National space agencies, drawing parallels between planetary protection protocols and deep-time research, should collaborate on dual mandates, preserving extraterrestrial environments and safeguarding Earth's subsurface record. Data sovereignty issues, especially relevant for anomalies found under contested territories, must be addressed through multilateral treaties that balance scientific freedom with respect for national jurisdiction. Simultaneously, we must consider the archival legacy we wish to leave. If Earth's dynamic geology can erase entire civilizations, how can we ensure that our own culture endures? The answer lies in distributed, multimedia geological time capsules, synthetic mineral matrices embedding encrypted digital libraries, genome libraries stored in desiccation-resistant biopolymers, and isotopic tags implanted at stable lithologies. These intentional signatures would serve as fail-safe calibrators for future deep-time archaeologists, should they ever exist, indicating not only our presence but also the ethical frameworks that guided our civilization. The dialogue between deep-time and real-time extends beyond Earth. Protocols perfected in subsurface reconnaissance will inform the search for life and intelligence on Mars, Europa, and Titan. The same geochemical anomaly detection methods, whether looking for CFC-like compounds in shale or for methane plume isotopic ratios beneath icy crusts, bridge terrestrial archaeology and astrobiology. Shared open-source architectures for data ingestion, anomaly scoring, and interpretive modeling create a unified platform for planetary habitability studies. Philosophically, acknowledging potential predecessors confronts us with dual burdens: humility and ambition. Humility in recognizing that our chapter in Earth's story is but one iteration among many. Ambition in committing to address the global challenges of climate change, biodiversity loss, and technological risks so our own traces do not vanish beyond recognition. This reframing of human exceptionalism into a continuum of sentient actors invites spiritual, theological, and ethical renewal. Interfaith dialogues might integrate deep time memorialization into rituals, honoring both extinct intelligences and future generations yet to emerge. Finally, the call to action. As researchers, educators, policymakers, and global citizens, we must cultivate what might be called deep stewardship. This ethos compels us to consider decisions not only in terms of decades or centuries, but across geologic epochs. Urban planning, infrastructure design, and resource management should all incorporate an awareness of Earth's capacity to remember or forget. Renewable energy installations, carbon sequestration sites, and even terrestrial art projects can be conceived as durable markers, intentional traces that signal our values to the deep future. A unified planetary knowledge network. Imagine a distributed digital commons, terra memoria, that aggregates real-time feeds from subsurface scanners, orbital sensors, citizen science reports, and laboratory analyses. This open database operates on interoperable data standards and FAIR principles: findable, accessible, interoperable, reusable. Each entry, from a radiometric date in a Permian shale core to an anomalous isotopic signature in deep-sea sediment, is tagged with geospatial coordinates, temporal metadata, methodological provenance, and confidence scores. Terra Memoria deploys blockchain-enabled audit trails to guarantee data integrity, while machine-readable ontologies allow researchers, educators, policymakers, and artists to query patterns across domains. Linking, for example, shifts in palynological assemblages to isotopic excursions and anomalies in synthetic polymer microfragments. Second, a transdisciplinary fellowship of deep time scholars. Beyond conventional professional societies, we propose the formation of the Global Deep Time Fellowship, GDTF, uniting geochemists, geophysicists, bioarchaeologists, AI researchers, ethicists, indigenous knowledge holders, anthropologists, and creative practitioners. The GDTF convenes regular symposia, both in virtual reality auditoria and remote field stations, to share case studies of promising anomalies, debate interpretive frameworks, and issue collaborative white papers. Crucially, membership criteria emphasize not only scholarly credentials but demonstrated commitment to open science, community engagement, and environmental justice. The GDTF also sponsors rotating deep time residencies that embed artists, storytellers, and philosophers alongside scientific teams in remote drilling camps, fostering cross-pollination where qualitative narratives enrich quantitative data. Pedagogical revolution. To cultivate the next generation of planetary custodians, curricula from primary to postgraduate levels must integrate deep time archaeology as a core competency. In primary schools, students learn the basics of stratigraphy through interactive sandbox simulations that visualize how sediments accumulate, erode, and transform over millions of years. Secondary students engage with virtual reality excavations of hypothetical pre-human settlement strata, analyzing synthetic samples and debating whether anomalies warrant claims of intelligence. At the university level, multidisciplinary degree programs in deep time studies combine field-based geology, computational analytics, ethics seminars, and speculative design workshops. Collaborative capstone projects challenge students to propose new anomaly detection experiments, draft policy briefs for global governance, or compose artistic works that communicate the poignancy of geological forgetting. A policy blueprint for deep time heritage. Drawing inspiration from UNESCO's World Heritage Convention and the Antarctic Treaty System, we recommend a multilateral agreement on subsurface memory, MASM. MASM establishes legally protected zones where intrusive subsurface research is regulated by joint committees of state, scientific, and indigenous representatives. It defines deep time heritage as any geological strata-bearing markers plausibly correlated with intentional technobiogenic activity. MASM also stipulates benefit-sharing mechanisms. If commercial entities or governments derive insights or materials from anomaly investigations, a portion of proceeds funds community-led educational programs and environmental restoration in affected regions. Dispute resolution channels and independent advisory panels ensure that MASM can adapt dynamically to new findings without compromising scientific rigor or local sovereignty. The stewardship of intentional legacies. Recognizing that our own industrial footprint may eventually be studied by far future explorers, we advocate the creation of designed geological time capsules at selected stable lithologies. These would consist of synthetic mineral matrices embedding high-density information repositories, diamond-like carbon crystals encoding multilingual histories, desiccation-resistant DNA-encoded libraries preserving biological and cultural archives, isotopically tagged bimetallic plaques that signal human agency. Capsules would be placed at continental craton sites with minimal tectonic activity and low erosion rates. Each capsule's location is recorded in public registries, terrestrial and orbital, ensuring redundancy against any single data loss event. Artistic and cultural reawakening. The quest for vanished intelligences galvanizes new forms of creative expression. Global art commissions, funded by philanthropic trusts and supported by the GDTF, invite artists to conceive installations that embody the tension between memory and oblivion. Imagine monumental echo chambers carved into resistant bedrock, where seismic vibrations from passing trains translate into haunting soundscapes, audible reminders that deep beneath us, the planet holds layer upon layer of erased narratives. Poets and novelists craft imagined dialogues with hypothetical ancestors, exploring themes of loss, continuity, and the resonance of choice across eons. Film and immersive theater productions stage unexcavated ruins using holographic projections, prompting audiences to confront what is seen and what might forever lie undiscovered. Ethical imperatives and community partnership. All deep time research must be predicated on free, prior, and informed consent of local and indigenous communities. Traditional custodians often possess oral histories and place-based knowledge that can guide anomaly searches towards sacred geographies or warn against disturbing sensitive ecosystems. Co-governance models ensure that data sharing and publication protocols respect cultural rights and intellectual property. When anomalies intersect with living traditions, such as ancient river courses still central to pastoralist narratives, researchers collaborate on joint interpretive frameworks that honor both scientific inquiry and ancestral meaning. Benefit-sharing agreements guarantee that communities receive training, infrastructure investment, and shared authorship on publications arising from their lands. Technological foresight and risk management. As we push the frontiers of detection, we must guard against dual-use concerns. Advanced subsurface imaging and AI analysis could be repurposed for clandestine military or mining interests. Accordingly, the GDTF establishes an Ethics and Security Council, ESC, to assess technology applications, certify research projects, and monitor compliance with MASM provisions. ESC issues risk assessments analogous to biomedical gain-of-function oversight, evaluating whether proposed fieldwork could inadvertently facilitate resource exploitation or ecological harm. Technologies designated as sensitive require additional layers of transparency, third-party audits, and community review. Bridging to astrobiology. The methodologies refined on Earth become templates for detecting extraterrestrial technosignatures in the crusts of Mars, the icy shells of ocean worlds, and the atmospheres of distant rocky exoplanets. Collaborative programs between NASA, ESA, CNSA, and academic institutions codify data formats, anomaly thresholds, and sample return priorities. Martian drilling missions include mass spectrometric payloads tuned to search for polymer fragments or isotopic shifts analogous to terrestrial technofossils. Observations of methane plumes on Titan spark reevaluations of deep-time gas anomalies in Earth's Permian deposits. By treating Earth and other worlds as a cohesive experimental network, we accelerate our understanding of intelligence's planetary traces.